Great. Thank you so much for this opportunity. Yeah, I'm currently working together with Tracy as our PhD candidate, and our so the first project of my PhD trajectory was regarding Gaussian transfer of learning abilities by use of diagnostic testing. So the project started as a conversation with some of the engineering programs at our university. And then for this one in particular, we focus on the case of electrical engineering, a program that is mathematically heavy, and the students of which are considered to be mathematically apt and in general also like mathematics. And yet, in spite of this, these students are sort of complain about or seem to not recognize previously learned mathematical concepts when asked to apply these in an electrical engineering context. So we, given that the students are mathematically apt, we focused rather than on maybe the students not remembering the mathematics, on rather their ability to really apply the knowledge that they have built with us in an electrical engineering context. And this focusing then on transfer of learning. Transfer of learning we took from two different points of view then. On the one hand, we can understand that as the application of knowledge learned in one context to a new context. This is the more classical understanding of transfer, and it has to do with us, the expert's point of view. On the other hand, instead, is the influence of learners' prior activities on their activity in novel situations, which is the actor-oriented transfer. So how students view this, if they recognize two different situations to be similar or requiring the same type of knowledge. With this focus on transfer of learning, we looked specifically at transfer from introductory calculus, so the very first subject that these students would have met at university, going into electrical engineering. And to test this ability, we developed a diagnostic test. And this diagnostic test was developed to contain a blend of mathematical and in-context questions. So the in-context questions, as we will see later, are meant to then test really this transferability, while the mathematical ones are there to, as a sort of check for us to see whether knowledge retention would then be a limiting factor. This we then implemented and analyzed and followed up with some interviews to clarify the data, making this shift from our point of view, so the classical transfer, to the student's point of view, or the actor-oriented transfer. The diagnostic test was created and designed in collaboration with one of our colleagues from electrical engineering, Chris Seinstra. And this was done in such a way that for certain, the in-context questions that we were using would match the knowledge that these electrical engineering students would have previously met in electrical engineering, while also being a good match for the introductory calculus knowledge that we were aiming to test. So we identified all introductory calculus topics, after which Chris made a selection of the topics most relevant to electrical engineering. We then provided some examples of typical calculus questions to him, after which he then designed a whole list of in-context questions for us. We screened these questions together with senior students. These were students that had already completed a bachelor in electrical engineering. And based on the screening, we made a selection of 8 different questions, which we then matched with a purely mathematical one, which was meant to be a close match in the sense of utilizing the same type of knowledge to arrive at a solution. So with these 8 questions, we then created 2 different versions of the diagnostic test, a version A and a version B. And I will try to explain how this was done. So given different pairings, we then divided these questions in such a way that both versions are a blend of both mathematical and in-context questions. And in addition, if for a topic the in-context question is in version A, then automatically the mathematical version of the question will be in version B, and vice versa. So each diagnostic test contains a blend, and each topic comes up only once. Again, in collaboration with the Department of Electrical Engineering, we were able to embed this diagnostic test as a pre-knowledge assessment to second-year electrical engineering students. This was done without a mark, so students who participated only got extensive feedback from us. This was also done to invite active participation. Eventually, out of 76 students enrolled for this second-year course, 49 participated, of whom 25 worked on version A and 24 on version B. Both versions were handed out completely randomly, with the care that if students were sitting directly adjacent to each other, either directly behind or next to each other, they wouldn't receive the same version. And finally, we carried out some quantitative and qualitative analysis, and later, based on these results, which were our interpretation of what students had done, we scheduled some interviews to clarify data findings. The quantitative results were obtained by use of a rubric that we ourselves designed, and that assigned to each answer a number of points from 0 to 4. With then the note that 0 was only ever assigned if students really did not attempt the question or simply wrote over what the question was. This was again also in the attempt to get as much data as possible. So at the beginning of the diagnostic test, students were specifically told to write as much as they could, even if it was just something like, I remember that the solution looks like such and such. So as you can see from these averages, in general, the mathematical questions are done slightly better than the in-context ones. But I must say that these results on their own say very little, which is why I will be going to the qualitative ones, focusing specifically on Q1 and Q3, both on ordinary differential equations, first order even to be specific. So looking at the qualitative results of Q1, you see above the in context version and below the purely mathematical one. So this is a first order differential equation, non-homogeneous. And interesting from the coding that we did for our results is that although the integrating factor is the preferred method taught during introductory calculus to these students, it was actually ever hardly chosen as a solution method throughout the diagnostic test. There were a few students that, as we had expected, attempted to separate variables, but many less than we had originally anticipated. More interestingly, a great majority of the students attempt a technique that we would typically associate with second order ODEs. So they find the solution as y is equal to y homogeneous plus y particular. And even more interestingly, rather than recognizing the homogeneous variant of the ODE to be separable, they simply guess the solution to be of form e to the power of some constant times x. Again, akin to the method that we would teach them for second order ODEs. Later in interviews, it was revealed that this is what students later on learn in electrical engineering, as for circuits in electrical engineering, this form, so with just a constant in front of the function VC, is the more common type of ODE that students would see. So this is the solution that they automatically use and reuse. And this, we found through interviews, then causes some type of backwards transfer, where students then change their previously learned knowledge from calculus based on later experiences in electrical engineering. Moving on to Q3, this is again a first order differential equation, but now separable. Here, the results were really different based on whether students had the in context question or the mathematical one. For the in context question, no correct separation of variable ever takes place. 4 students correctly guessed the answer, again in a similar way to done in Q1. So some e to the power, in this case, minus lambda times t. But the great majority of students do attempt separation of variables, but simply incorrectly leave n of t on the right-hand side. Interviews then showed that this was due to the fact that students aren't used to the notation n of t and rather to simply n and then t written completely separately, and so seem to struggle with recognizing where this term would belong to. On the mathematical side, we see something really different. Here, students were quite successful at both recognizing the type of ODE and solving it. 14 out of 24 students correctly separate variables. There are then 4 that mix terms, making integration a little simpler. And then there are 3 out of 24 students who first correctly separate variables, but then differentiate rather than integrating. So comparing the 2 questions, so as you've seen, we've gotten lots of different results from analyzing the 2 questions as they are currently posed. There are some adjustments that we're planning for next iteration based on some of the insights we got from the interviews. One thing in particular is that currently we feel that the mathematical version of Q3 isn't the greatest match for the in context one. Particularly, we would like to remove this divided by x and see if then students still are able to correctly separate variables. The other thing that we've noticed or that has come up in interviews is that there have been students that correctly solve Q1, again with this method of first finding the homogeneous and then the particular solution, and in doing so, solve the homogeneous by simply guessing the solution e to the power of -1 divided by RC. But these same students then don't recognize that the same method would apply to Q3. When asked to compare the two, students mentioned that they could clearly see that Q3 was separable based on the fact that rather than n of t apostrophe, the notation here is dn of t dt. So even more interesting, maybe for our next iteration, would also be to change this notation to be n of t apostrophe and see if then the results change. So whether in that case then students would be more successful in the in context version of Q3 rather than the mathematical one. Yeah, so as a short conclusion then, so again, diagnostic test in its current form is really informative, and it gave us lots of insight about student solution patterns, and particularly also about some of the weaknesses in our study material. So I mentioned the unproductive backward transfer from electrical engineering, where students essentially see these examples so often and have to use the solution so often that they don't realize anymore that this is a very specific case of something they had previously learned. And there is this recurring calculus notation. So for specifically separable ODEs, very typically students would see in exercises this notation dy dx rather than y apostrophe or y dot. So there is some notational variation that we should be bringing in to aid the students in generalizing their knowledge. And so improvements for next iteration, again, would be this notational variation and this closer matching between items. And eventually, this will be probably expanded also to the course in general, trying to really aid students in understanding when something is a very specific case of something and when notation is equal to one another. This was briefly an overview of my research.